You've probably heard the term inductive kickback tossed around in electronics forums or flashy TikTok builds, often described like some mystical surge of energy from nowhere. But here's the thing, it's not magic. It's real physics. And it's actually one of the most powerful, misunderstood forces hiding inside your circuits. Let's break down what it is, why it happens, and how it can either boost your design or completely fry your components. An inductor is simple at first glance. Just a coil of wire, often wrapped around a magnetic core. When current flows through that coil, it builds a magnetic field around it. But here's where it gets interesting. Magnetic fields, just like stubborn old habits, don't like to change. That means if you try to increase or decrease the current suddenly, the inductor will fight back. If the current through the coil is steady, the inductor doesn't care. It just sits there doing nothing like a regular wire. But if you try to shut it off suddenly, that magnetic field resists the change hard. It generates a force to keep the current going in the same direction, no matter what. This is what we call inductive kickback. When current is interrupted in a coil, the magnetic field has nowhere to go, so it collapses. And it does this almost instantaneously. That represents a near infinite frequency change. Think about it. Frequency is about how fast something changes, and if the magnetic field collapses in 0 time, that's, well, pretty much infinite. And when you pulse a coil really fast, the coil develops something called inductive reactance, a kind of frequency-dependent resistance. It blocks most of the current at first, storing that energy in the magnetic field instead. It's like the inductor says, "Nope, I'm not letting this current barge in so fast. I'll hold on to it until I'm ready." Now, here's the kicker. When that magnetic field snaps back, it slams into the resistance of the coil with force. But there's no current yet, only pure voltage. The inductor's energy is now looking for a place to go, and if there's a path, it will convert back into current and power the load. But if there's no path, it will jump air gaps. It will arc across switches. It will burn through components, because the current through an inductor cannot change instantly. It will find a way. People call this an inductive voltage spike, but that term doesn't do it justice. This isn't just a spike. It's stored energy under pressure trying to break free. The higher the inductance, the more energy is stored. The lower the resistance in the path, the longer it can hold the current. And the faster the current is interrupted, the sharper and higher the voltage. This is why even a small inductor can blow the lid off a transistor when switched carelessly. Let me emphasize something else. When you flip a switch, that transition from on to off isn't some smooth fade. It's instant. There is no real time between on and off. And even the tiniest physical distance inside the switch, like microns, becomes critical. Because the magnetic field doesn't wait. It collapses right now with nowhere to go. And that's when voltage spikes strike. Let's say you have an inductor connected to a battery. Once you break the connection, the inductor tries to push current through whatever it can, even through the air, across an open switch, or through nearby circuits. That's where the danger comes in. These unexpected voltage spikes can cause transistors to break down, microcontrollers to reset, and switches to arc or weld shut. This is why inductors are both powerful and risky. But when used properly, inductive kickback becomes a tool, not a problem. This is how boost converters work, converting lower voltages to higher ones using controlled inductive collapse. It's also how ignition coils work in cars, generating 20,000 plus volts from a 12V battery to fire spark plugs. In fact, most power supplies rely on this principle. They just control it precisely with switching regulators and diodes. To avoid damaging components, we use things like flyback diodes to safely route kickback current, snubber circuits, Zener diodes, or TVS clamps. These all give the collapsing field a path to follow, one that doesn't destroy your transistor or burn your board. Because if you don't give that energy somewhere to go, it will find its own way. So next time you hear about inductive kickback and someone makes it sound mysterious or supernatural, remember this. It's not magic. It's not free energy. It's not a loophole in physics. It's just a coil doing what coils do best, resisting change, storing energy, and snapping back hard when you try to stop it. And if you understand that, you're already ahead of 90% of people out there.